Hi folks, today we're looking at graphical solutions to trig equations. As always, there are downloadable notes in the video description below, as well as a worksheet for once we're done. The big idea here is that for graphical solutions, you're finding points of intersection between two curves. And that means that you're going to graph the left-hand side of the equation and you're going to graph the right-hand side of the equation and see where they meet. It can be done by hand, but it's hard to achieve a great deal of accuracy. So we're going to focus on the use of technology, though we will try and freehand a couple of them here. So graph each side of the equation. The x values of points of intersection are solutions. Now, it's worth saying that we're not going to get a whole lot out of this if we don't know anything about trig functions to begin with. So it would be helpful to know what the graph of sine x looks like. So here we go. We've got sine x equals 0.4 for 0 to 2 pi. If I were to graph sine x from 0 to 2 pi, here's what it would look like. If I were to graph y equals 0.4, here's what that would look like. Okay, because we know this is 1, there's 0.4. Okay, somewhere here there are points of intersection. Wherever those are x values that satisfy the equation. We could do this on a graphing calculator, or I'm going to go to some graphing software. This is desmos.com. So if we go ahead and graph sine x, so we just go over and we click functions. There's sine x. There we go. And the other graph that we want is y equals 0.4. Okay, now you can see that I'm seeing too much of the graph. All I wanted from the original equation was from 0 to 2 pi. So I'm going to change my graph settings so that I only see that. X-axis we only want from 0 to 2 pi, so that's 6.28. The y-axis, we don't really need to see so much. Let's just go from -2 to +2 because a sine graph only has an amplitude of 1. Okay, and there we go. The solutions are just the points of intersection. So that happens at 0.412 and 2.73. Easy as that. 0.412 and 2.73. Let's try another one. Cos x is -0.7 from 0 to 10. Now I could try and freehand this. Cos is going to look like this. This would be 2 pi. I'm going to see another cycle and a bit. -0.7 would be down here. I'm not quite sure if I'm going to see a fourth solution crop up. But that's more or less what the graph's going to look like. Let's take a look at it on the graphing software. So instead of sine x, we want cos x. Y equals cos x. And the other one was y equals -0.7. Hey, now change my graph settings. I need to see this time from 0 to 10. Okay, and now we can see that there are solutions right here, and right here. Those are all solutions. So 2.35, 3.94, and 8.63. So we just write them in. X equals 2.35, 3.94, and 8.63. Okay, let's just do another one. Sine x equals 4 for 0 to 20. So I'll go in and put in sine x. And the other one is y equals 4. I'm not seeing that y equals 4. I need to change my graph settings so I can see up to 4. And it also wanted me to go from 0 up until 20. Okay, there it is. Now you can see down below there's the sine wave, and up above there's our line. Are they ever going to meet? No. They're a horizontal line and a sine graph that are out of touch with each other, so there are no solutions. Okay? The x values of points of intersection are solutions, and if there are no intersections, then there are no solutions. Getting general solutions out of this is a little trickier, especially if you don't know a whole lot about sine graphs and cosine graphs. So general solutions from graphical methods look like this. You just add period times n to each what I call different looking solution. Okay, so we'll see that there are recurring solutions, but we only want to consider each different looking one. Otherwise, we'll have redundant stuff. Recall that the default period of sine and cosine is 2 pi, and the default period of tangent is pi. And I'm just saying here, to appreciate a general solution from graphical form, you'll need to learn about the graphs of sine x, cos x, and tan x, and their various transformations. So right over here, sine x equals 0.4. Well, let's go back and solve that graphically. It doesn't really give me a domain, but I can see that there are a whole bunch of solutions. There's a solution right here at 0.412 and at 2.73. Now, if I go over here, that is actually just a repeat of this solution back here. So the only two different looking ones are at 0.412 and 2.73. But they recur with every period. And the period of this function, since it's a regular sine graph, is 2 pi. So they recur every 2 pi units. And that looks pretty familiar from what we've done with general solutions already. We could have a case, though, where the period is not 2 pi. So in this next one, cos pi over 6x. The way we figure out period, it's always 2 pi divided by whatever's in front of the x. And again, if this is new, that's okay. That just means that there's something else to check out in terms of trig graphs. So this would have a period of 12. Let's go and graph this. Cos x, cos of, we want, maybe we'll open another set of brackets, pi divided by 6. Yeah, didn't need that. X. Okay, and the other thing we wanted was y equals 0.2. And now let's go look at the graph. You can see that it's got a solution right here and a solution right here. Over here it has another solution, but it's just a repeat of this one back here. Okay, it looks the same. It's a down part of the cosine curve. So we have 2.62 roughly and 9.39. Let's put those in. And we said that the period on this one was 12. So we'd have 12n plus 12n. And in all of these cases, n is an integer. Let's think about what that might mean. If that's the general solution, then if I put, say, 1 into this one, I should get 2.62 plus 12 times 1. If you go over here, that's actually the value of this next solution. If I added 12 onto 2.615, I get 14.615, or 14.62. So when we write these out with the plus period times n, it's giving us all the potential solutions. There are a few practice problems, if you like, in the video description below. In our last video on trig equations, we're going to look at operations that happen to the angle so that we can deal with stuff like this one over here analytically without the graph. See you soon.